Hello, folks. Hope that today's treating you well. It is the last day of May. It's not gonna be May tomorrow. Yeah, last time we were kind of recovering. Um, basically, the video before last, we horked up our city. We did. I think we think it's like Bede's version upgrade that caused a migration that caused our adult DB to be unreadable. And I sort of hammered through that for a couple of hours and played some puzzles, but mostly just hit yes, vanilla Claude, just do it, just do it, just do it. Um, Probably a dangerously allow all permissions kind of situation. Since our work is being saved off in private Git repositories, uh, there's not a whole lot it can do to screw us up at this point. It won't be too bad. And then in previous video, I cleaned up some of that stuff offline. We got the city running again, and now we're in the middle of doing some actual work, more or less. We're trying to promote a couple hundred designs in our catalog, and we're going through vocabulary additions one by one. I'm gonna have to see if I want to keep doing these beads. Like, I think there are 30 of these, and we stopped after about an hour total, and we'd only done like a couple of the vocabulary additions. But for my own edification, I was going through them kind of slowly because the beads are using sort of highfalutin language, and I want to understand, what kinds of additions we're making, how they help us classify puzzles, because that's how we're going to be using these as kind of the mechanics that have been done to death or that have never been combined before. And it's important to understand like how different flavored they might be, whether there are mechanics that are sort of parents of other mechanics. One of them, for instance, was like locality. Local clues is sort of a superclass of like local counts of nearby things and local properties of nearby things. Might be some like children of that. And there's all kinds of ways, things that we might learn by going through these kind of slowly. So let's keep doing that. And so I think we were literally stopped the video right on as we were typing this, and I had to go do some personal stuff. Um, let's see, what was I thinking? Perfect matching of placed objects. Um, so I was thinking kind of about injection, surjection, and bijection. So these are sort of like mathematical properties of functions where um, every input maps to an out. So everything in the domain maps to something in the range. Everything in the some every I'm saying these wrong. Um, uh, and it's been a really long time since I took that class, 25 years, maybe longer. Um, so it's sort of like everything in the domain um, it is has a value when you put it into the function, and some of those values get into the range, right? Not every value in the range is used. There's another kind of function where some of the values um, are used in the domain, and then they map to all of the values in the range. Um, so, for instance, maybe rand is a good example, right? Um, you know, that's not a great example. I was trying to think of something that could have more than one potential output. Rand is one of those things, but not a great example. And then, because I think that, and then there's bijection, right, where um, every input maps to an output, and then every output maps to an input. So like an invertible function, right? Um, Bijection, injection, surjection. Um, Curious if we will see that eventually in the corpus. All right. I think we were getting close to done also on the instruction book for World Puzzle Grand Prix. It is still open. There are still like 3 days ish. I think we maybe a little less than 3 days now to go and do the puzzles. And we've been trying to go through all the different puzzle types and ensure that for each one we have a sort of at least an understanding of the mechanics and the strategy, that kind of thing. And so we left off. Hex Slitherlink went really fast. I've been able to practice those at home, and yeah, no qualms there. So we started working on Compass. Compass is more difficult for sure. Interesting one, I would say. Um, we don't have any really strong strategies for it yet, I wouldn't say. Let's see here. About 300. Okay, that's pretty good. Um, so briefly, the point of Compass is that we're going to have 5 regions, and we're going to divide this 5 by 5 area into those 5 regions, and we know that because we've got 5 kind of clues. So like each clue is in the region. Like this is the B region, this is the A region, um, and so and we deduced last time that there was no way for any of the regions to reach this other than A. Uh, and we know that it can't that this one can't be B, and there needs to be a barrier between whatever region this is and B. And then we also know that this region has to have a sort of orthogonal path out of this little corner, and so it's got at least 2 cells, and that eliminates. We know that for it to reach to C, it would have to take more than 2 cells to do that. um, Cells above the line, right? Above the C line. So some of the we we know from this clue that we go anything north of the line that borders the north edge of C. There's going to be 2 more C's somewhere in this. Now 6 cells. 2 of them will be C's, exactly 2. And we're not sure how you get to them. Maybe you go this way and then you go up to this corner, or maybe you go straight up. Maybe go like this. We don't totally know yet. But yeah, we have to satisfy all of these region properties at once, and we're trying to do that in a well motivated way. Um, and then you can see we've got all of the other region properties to balance, right? There's at most one B. We know that this can't be B, for instance, because it would have to escape up this way, and that would require more than 1 cell to get out. I guess anything down here, down below these two, we can assume can't be B. Right? So we're going to have one B somewhere on this row. This definitely can't be a B. I don't think there's any way that we can draw a path to get to this corner from A, because 1, 2, 3, 4, no matter what, we can't get like a path of 4 from this row down to this corner. So B and E can't do it. Um, C and D and E, I think, are the only possible options, right? And so I think that the way that we can do this puzzle is by like examining each possibility for these important squares and asking ourselves, can we get there? Um, so for instance, up here, it's possible for D to get here because there's no restriction on D. It wouldn't be possible, it's barely possible to get C over there. 2 to the, well, no, that's not possible. I'll explain why. So say this was a C, then just by the same corner thing, there'd be a barrier here between C and A. There'd be another cell for C, and then we would actually used up all of our quota for C. Like we can't get any other cells to the left of this line, and we can't get any more cells up from this line. So this definitely can't be a C. There's no way for it to be a B because that would be up here. There's no way you can get an E path to reach. So this one's got to be A or D. And we can kind of continue on in this fashion, right? Uh, and there are like multiple potential ways to think our way through the puzzle. Um, for instance, we could just try some experiments and say, well, if we took our three E's just like so, we could fit our two D's in here. Um, and then we'd have still one more E to go. And we could put it over here in this corner. We have these sort of two countervailing things, which is every single square needs to get assigned, and then every single clue of all these regions needs to be exactly satisfied. Hmm. This is a kind of interesting way to look at the puzzle, I think. Let's take a look at this region here that's 3 by 4. A lot of things have clues in this arena, right? At most, 4 of them could be A's, because if the A's went this way, then even less of them would be A's. At most, 2 of these 8 can be C's. At most, 3 of these can be E's, right? Hmm. So that only accounts for like 9 of the cells, and they all have to be labeled differently. So it's like we could have at most um, 3Ds. I wanted to say at most, but I think that's not true. At least, at least 3Ds. There's no way to. Well, B could kind of sneak in here this way. Another interesting way to think about this is like how do we get say that B were over here. It would have to stretch across this way. Um, then it's pretty hard to start getting two C's, right, that are to the left and above. We could go one to the left, and that would be one. We could go two, that would have one above, but then the two to the left is used up. And because this is blocked off, um, we're not able to, do another cell to satisfy both of these restrictions. Uh, and I think the same problem with A, right, being here, right, is that, well, I guess as long as we could get this sort of sneak the C over here, that would be one above the line, and then we could do maybe these two, and that would satisfy those clues. Hmm. 2 out of these 4 have to be D. Kind of interesting. That means 2 have to not be D. There is a sort of, if we got a D all the way over to here, that would be like D, D. We have to somehow make it back to D. Maybe this way. uh, if we did this, though, there'd be no way to satisfy both this E and this D, because it would need 3 to its left. Well, number one, it has to have at least one of these to get out of the um, this bottom row here, because it needs to get to go up 3 times. So if we cut it off, if we put D here and then we sort of have to either go this circuitous way around or which seems unlikely. Uh, yeah, or we just can't do it. Like, well, yeah, yeah. So there's no way to make all of these D. I mean, it would be like a big around the world kind of thing here. And then you couldn't satisfy the C if you did that either. I'm tempted to say there's no way to put a D here. That's not like a proof, but it's like an intuition. All right. Okay. It captured something about bijection, injection, surjection. Great. Assign digits to symbols. Satisfying an arithmetic equation. Yeah, and yeah, yeah. So this is about decoding letters as numbers, and that's a mechanic that could be used in other puzzles too. Um, I think um, pure cryptorhythms I wouldn't classify. I wouldn't. I would classify as logic puzzles, but not 2D ones. And but it does seem it is a mechanic I have seen used. For instance, solve the cryptorhythm in the context of Minesweeper, where the letters stand for local count, mine counts. Incorporated into the puzzles. All right, yeah. So we have seen that 14 Minesweeper variants. Two, I think, as those ones. I think we're probably going to agree on that. We were talking about how hard it would be to assign a D down here. We can't get B here. C would be possible, or E. Those are the sort of main two candidates. This area is kind of crowded because we need to get A down to the rest of the puzzle, potentially like this way. And we need to get C up. Um, if this, I think we were sort of deciding that if this isn't a C, then there are big problems. Let's just try and go with that for a little bit. Um, again, it's not in the nature of a proof. Um, in order to keep this A from being cut off, it either has to do some really circuitous stuff or just go through here. Um, hmm. Then we're trying to talk about this. I don't know if drawing the lines is helping that much. I don't know. It's like I feel like what you want to do for this puzzle is write certain probes, right? Say like if I don't make this a C, does weird stuff start to happen? Yeah, yeah, I mean it definitely does. If I don't make this if I make this an E, for instance, let's try that world a little bit. This has got to be an E too. And then we'd have to conclude that this was a D and this was a D. Um, that world doesn't seem to be working very well, right? Like, I think that in fact their curves have to cross each other. Um, right? We've got to get this E to cross these D's, and this D goes like this, and now we've got a really long. Well, we've even got it blocked off, right? Like we're saying that like we can't get the E through this wall. So we could conclude that this isn't an E. Basically, the only candidates left are C and D. C has this same kind of problem, right? C, C, D, D. And we don't have a. Oh, but look at what happens with C, right? There's two C's to the west of C. So none of this is C. This has to be D, and then this would have to be a third C. It can't be C. So this is an even better probe, I think. Actually, D. Now we only get one more D, and we've got to. It's got to be. Say it were this one. We would have to get back to these D. This is not a D, so something else has to come out of here, and then it has to go like so. And right now it's sort of cut off from the rest of all the D. We'd say this can't be D for sure. C and E are the only likely candidates, I think. Yeah, the other ones, A and B, just can't reach this far. Um, if this were D, we would start running into those long difficulties. The only path through here, assuming that this C is right, which I am for the moment, we'd have D, D, and then we have to get through this part right here. And then no matter what, we'd have the E coming out this way, and the D would get cut off. So this can't be the D, I don't think. We're left with C and E again. C is in an interesting spot because on this side of the puzzle, it can kind of go everywhere and do whatever it wants. It's possible that that these E's kind of cut off over this way. Maybe they go like this, 1, 2, 3. And then we need another one up here, perhaps. C would have to sort of snake around this way. The problem with that is it's hard to get B to work like that. Like B is already kind of cut off. It's going to go here or here, right? And so if E goes here and it doesn't go here, like if C, let's start putting C's in. If C goes here and here, oops. Uh, if it went here, it's pretty difficult for B to get off the ground because we've got to say this isn't a C, say it's an E, right? Then the C's go all the way around, and there's actually no way for B to escape. So this couldn't be an E. It would have to be like a D or a C, perhaps. Uh, if this were a D, it's no helps. The C still blocks off the B. So it has to be a C on this hypothesis, right? That we're starting from C in the corner. And then it can kind of get back to the C in one of these two ways. One of these two cells has to be a D. And then this, we have to get 3 to the left of this. So it kind of has to escape. But the problem is that there's no way to get 3 to the left and 3 above on this E, right? If we sort of start charting a pathway this way, we run out of west squares and we haven't satisfied our north squares. So I think either way, it's impossible to make the C work for that corner. If, let's see, if this is going to escape into the west somehow, um, if this is D, then it's problematic to put anything else in here. It was sort of cut off the D from its own D. So I think it's got to be like so. This last bit, if it were C, then it would cut off E from the west. So it's got to be E as well. We're trying to get E to the west here. This is really our only choice now. And maybe a third one. Those aren't totally forced moves, but pretty close. And now we can kind of choose this one or this one for E. We need to get 4 A's down here somehow. I think it's more natural to do sort of like a 2 and 2. Like if it's these 4, then there's no way for C to advance to the west. So we've got to start going over here. We were talking about this hypothesis before. Let's just try it and see if it works. We left room for our 1B. The problem here is that we can't fill in both of these last two squares. Um, because, well, actually, what's the problem? If this were a D, I guess that kind of works actually. We fill in this one, maybe with an A. This one with an E. There we go. We've satisfied our 4 A's, and we've satisfied our 3 E's, our 3 west E's, our 2 lower D's, our C's, our B, and now we're left with sort of like a free hand to draw a D here, an A here, and an A here. So I think this works. This does like divide the regions appropriately and satisfy all of the clues. Now, did we draw like a straight line to all of the like inferences that we made? No, definitely not. And so I wouldn't say, oh yeah, I've really understood this puzzle type or we solved it. Like the fact that it works at all is cool, but yeah, and it does match their solution. Um, but it's more by virtue of the fact that we couldn't come up with another solution. Okay. Optical beam reflection tracing. Uh, I really hate this stuff. There are certain puzzles like there are mirrors in the field, and you're trying to determine what can be seen with those fields, that kind of thing. Um, we can count how many rays are hitting a certain spot, or um, we sort of probe like, what can I see from here? That kind of thing. Um, so personally, I don't like them. Mhm. Yeah, I guess so. Yeah, approve as well. Um, ray rays rays with mirrors might be a subclass of rays in general, e.g., the rays in Akadi lanterns. Um, why am I putting you through all of this? Why are we looking at all of this stuff one by one? What are we learning? Well, we are kind of developing our expertise about this design area. Um, and we're trying to see what's been done. That's great. Um, it's an example of the kind of domain specific knowledge that we're trying to cultivate, right? And if I give it a bunch of examples, or if I go through the examples and I say, okay, here are my observations, like after a while, it's going to suggest things to me and it's going to say, we don't need to. Um, for coloring. Yeah. I don't know what Yagi is. Let's look at that one. I am certainly familiar with like four coloring. So there is a puzzle in Simon Tatham that does just four coloring. We still haven't finished that logic puzzle, by the way. Um, I guess my advice, if you want to finish a logic puzzle, have a pencil and paper. It's very difficult to reconstruct a lot of those thought processes inside of a notes field and without undos and stuff. So, yeah. Simon Tatham does have the mirrors in here somewhere. Here's black box right here. Um, if you know the numbers on the side, can you find where all of the ball has to be? And you sort of probe by flipping over each these side clues. They're not usually given at the start. In this one, it's sort of like an interactive puzzle. Yeah, so you can see like here I probe and like there's got to be a ball right here because somewhere on this row a beam hit a ball dead on and stopped. Now will sort of probe again, and we watched as there's some ball that caught a couple of balls, perhaps here and here. Um, if you go next to a ball, then it bounces off kind of the corner 90 degrees, and diagonally next to it would bounce off the corner again, and it came in here and out here, something like that. Um, Not my favorite. It's sort of like you have to think of it's sort of like an optimizer game where you're like, I want to click as few cells as possible to deduce all of the balls in this thing. Um, so for instance, if I try here, so this is kind of an interesting thing that happened here. Like, we know that the two balls that are causing this reflection thing are not on this row because this row caused a deflection over here. So you could hypothesize, for instance, that there's a ball right here and that somewhere else, either down, lower, or up, well, couldn't be along here. Uh, Maybe we'd want to do stuff like this, right? But yeah, we're sort of looking for a couple of balls that are going to be the corners for this to reflect off of. So we've kind of taken care of these two clues, though, just with our sort of simple hypothesis, right? So this one says it's going straight through. We would hypothesize that none of those were used. So this one, we'd sort of hypothesize that there are no intervening balls. There's two balls somewhere along here. Well, have to be both of these sides, actually. Why am I getting so distracted? No big reason. Um, but yeah, maybe up here, or even here. I don't know if that one works. I think that one just would make it like a reflect backwards. Right? So it's one of these two. We could try to do that. So this one horizontal, it hits. We could hypothesize that this is where the ball went. We could test that hypothesis sort of like so. This one, it's sort of like bouncing off of a corner, right? So maybe we want to change our hypothesis a little bit. This is a way to do it, and we only get 5 balls to make all these observations with, right? What's the most revealing hypothesis left to us? Maybe like so? Okay, that's a good one. But see, we're not done. We haven't eliminated all the other possibilities. So how are we supposed to do that? This one says there's definitely a ball in this row. So something's wrong, right? We don't know exactly what, but we could guess. So one for instance is like the balls are down here. And there's some ball along this row somewhere. And it wouldn't be in the path of this 4. I mean, we're sort of trying to decide between are the balls on this row or this row. Oh, that's an interesting one. That puts the ball here and here, not here and here. Right? Okay, so looking at all of our clues, it works for the 4s, it works for the 1s, it works for the 7 and the 5. So this is pretty strong, I think. We don't know about this horizontal one or this horizontal one. We could eliminate all of these other ones, right? It's got to be one of these two. Because nothing else is on the line for this to be horizontal, right? We could try this one. That wasn't very helpful. Okay, that one was helpful. It caused us to believe in a bounce right here. And then there's one more on this line. Well, I mean, this one could have happened just due to hitting this corner and then hitting this ball. So we're still about like one ball short. Okay. So we'd know that it didn't get all the way to here, because if it did, then it would have reflected out the puzzle like so. We could believe in this ball. There we go. But yeah, you can see how it's kind of messy and like I don't know. Not my favorite. Yeah, I get it. Sheep and wolves. Draw border lines so that each region contains only sheep or wolves. The borders are polylines. They can only turn at the designated black grid dots. This is like palisades, right? And may cross themselves only at non-black dots. Okay, so hmm, there are border sections, I guess, and some of the border dots have been filled in for us. Cool, interesting. Uh, yeah. Um, yeah. And it is less about coloring and more like partitioning, as in, let's see if they documented the name for Palisade, the annual 5 cells. Here's the 4 color thing inside of Simon Tatham. So we know by the 4 color map theorem that there must be a way to color any map like this one that has, that meets at vertices and that kind of stuff with no more than 4 colors. And in this puzzle, we've also been guaranteed that there is exactly one 4 coloring given all the given information. And so we've got brown, red, yellow, and green. And for instance, we can see that brown, green, and yellow are all touching this region, so it has to be the 4th color. And then we can kind of take it from there. Okay. Um, we'll revisit in number 20, one of the other beads. Uh, okay, I think we did see this one before. Hmm. Maybe we're talking more about symmetry here. There are some other puzzles that require regions to have rotation symmetry. Congruent component shading. Uh, this would be a subclass of that. Okay. Slowly, slowly, slowly. Okay. All right. Here's the puzzle. Next puzzle. I think we're getting close to the end. Is this the last one? Yeah, I think this is the last one in the instructions. So once we read all these instructions, if you've been faithfully following these videos, including, well, I haven't published the 3 hour one yet. It's like on its way to YouTube. But, you too would have all the tools you need to solve all of these puzzles. Divide the grid, we'll just try not to look at the answers. Okay, divide the grid along the dashed lines into regions, polyominoes. Each polyomino must contain exactly 2 numbers, and the area must be between those 2 numbers. That's interesting. Some numbers may be prefixed with less than or greater than. The polyomino containing those numbers must have an area less than or greater than that number. Okay, so if it doesn't have an operator next to it, then it doesn't tell you like whether it's supposed to be less than or greater than, you have to deduce that from the other one. Okay. What about the dots? What are those about? For each dot, determine which polyomino it's in and enter the greater of the two numbers in that polyomino, ignoring the prefix. Read the dots from left to right. Ignore the row that the dots are in. Oh, okay. So they're in one of each 5 columns. We're placing them in their regions, and then we're taking the greater of the number of regions. Okay, so the dots are just for the answer determination. They're not part of the puzzle, really. Okay. So the kinds of things that we're doing are things like whatever region we pick here. Let's start with this 2. The region's going to be between 2 and either 4 or 5, but not both. And whichever one we pick, we're not picking the other one. We're drawing a line in between them. If we put these 2 together, we'd have to draw a line between, or a region between 7 and 8 large. We've only got 25 to play with as well. So if we make a region of 8, like maybe in this corner right here. Oh, the other interesting thing, just stay with me for a minute. Let's pretend that we made this region of 8. It causes some problems because no matter which numbers we choose, well, I guess we'd have to go like this. Uh, Perhaps like that or like this. It can't scoot out to any of the other digits. We can't get the third number into this region. So we probably have to pick starting from, well, we could do this one, but then this region has to be between 5 and 6. Uh, yeah, this kind of thing, right? We definitely can't make this one connect up with greater than 5 though. So this way is not working, right? But yeah, we were forced into some things by not being able to get a third number into the region. So that sort of suggests that the right place to start is with this 2 right here. And basically, it's the first region, whether it takes the 2 or the 4, it could at most be 3 large, including this dot. And then, depending on which way we go, we're forcing another region to be made. So there's a few different hypotheses that we've got available here for this 2. We've either got 2 and 5 are together alone. We've got 2 and 5 incorporate the dot. We've got 2 and 4, and we've got 2 and 4 incorporate the dot. Let's look at this 4 one. We need 4 or 5. We can't have a 6 in there. Got to be between 4 and 5. It's definitely would include like these 3. It's ambiguous whether it would include this last dot or not. We have this greater than 5 and this 8. Greater than 5, less than 8 would be a possibility. 7 and less than 7 I don't think can go together. Between 7 and 1. 6 and less than 7 could kind of go this way. We're just trying some silly stuff here. Is this a valid solution? This is between 5 and 8. This is between 1 and 7. This is between 6 and less than 7. This is between 4 and 5. And this is between 2 and 5. I mean, did we learn anything? I don't know. The greater numbers here would be 8. This next one would be 5. This one would be between 1 and 7. This one would be between 6 and 7. This one would be between 4 and 5. Is there some reason why our solution doesn't work that I'm not seeing? The blue solution here? Let's look at some other rules. Each one contains exactly 2 numbers. Check. The area of the polynomial must be strictly between those 2 numbers. I think this one is a problem because it's not greater than 6 and less than 7. This is probably the problem right here. And this one, we can't do between 4 and 5 either. This is the real problem. Like, it's very hard to fix this part. So that's probably the issue, is that, yeah. Well, I think that's an interesting point too, because it actually means we can't put between 4 and 5. Those can't be in the same region. And we can't be between 5 and 6. So that's nice. That actually tells us some interesting information. We also can't be between 7 and 8. If you want to be between 2 and 4 or 2 and 5, you can't have exactly 2. You've got to include this dot. And then you have to stop there. So we could actually put this in. There's actually no way for the 4 to escape, so we'd have to do it with the 4. All right. And then this would keep going like this. All right. So yeah, a lot of the numbers are already spoken for, and we've gotten to make some logical conclusions here. This area's got to be 6 or 7, right? This one's got to be, it's not obvious, but if this were 6, oops, sorry, I'm not trying to reference the solution. If this were 6, we could definitely include this one between 5 and less than 7. We can't do between 5 and greater than 5. And any other numbers are going to run afoul of like overlapping curves. So to me, that says we've got to get to less than 7. There's really only one way to do that without interfering with the rest of the puzzle. Yes. Greater than 5 and less than 7, we're going to have to do, like, we're going to have to get 6 out of this region. Right, this one between 1 and 6 is kind of free, and we can kind of design it last. And we need to have at least 6 for this one in the corner. It sort of suggests intuitively like this. We believe that these two don't connect. We got 1, 2, 3, 4, 5, 6. Yeah. Okay. So this between thing, strictly between, is probably the key rule. Okay, so now we've got an 8, a 4. This one is a 7, 6, and a 7. Okay, great. And that does line up with their answer. Okay. It was a little loosey goosey, I think, especially like the 5 to 7 inference. But I think that we were started evaluating it against like the curves, and we knew that we had to get to here, and we knew that we were lying out here, and we also knew that every cell needed to be used. So we were kind of doing a number link kind of thing there, where we can't make the streams cross, and we've got to use the whole grid. All right, cool. That's the last one, last puzzle. All right, functional graph routing to sinks. The directed graph must be a forest with the goal cells as roots. Yeah, that's good. That's good. I recognize the mechanic from Nicole Golf. Nicole Golf. I don't think that one is in this list, but it's probably in. I feel like we did one of these. English Wikipedia, I think, has got the list of puzzles. Mm. Back to Yanko. Um, this is making the symmetrical. But it looks familiar because here we go. Hell golf. Herugolfu. This one, right? Is that what it's called in the staging catalog? That's interesting. Why don't they have this? Is it in here? Here it is. Chain with cell numbering. And here we go. We need to route. I guess we could go. We could like look at Roma too. Sign 1 of 4. Directional symbols. Each bordered region holds at most one arrow of each of the 4 directions. And then I guess it's sort of like a vector field of wind that's going to blow the ball into the right hole. Mm-hmm. The whole grid is a functional graph. Okay, I see. labeling the labeling the whole field is the big distinction, I guess. Okay. That's cool. Hmm. Guess that's your hydration reminder. We're at about an hour into the stream. Uh, let's see. I don't think I've posted this in the. Let's pin this again. At least I think it's pinned in the chat once again. Yeah, it's the instruction booklet for the current round of the World Puzzle Grand Prix. All right. Constraint is a fixed point condition over the assignment. Oh, yeah. This one seems to be the same kind of thing. If I place a number, then it's in a region that's exactly that size of number. Philomeno. Seems to. We don't want staging. Oh, oops. Look at entries. Defined by new. Hmm. Yeah, so as a reminder what I'm talking about. And I think the hardest part has been like knowing the Simon Tatham names for something and not knowing the exact way it's stored in our catalog. Is this my job to shouldn't it be looking at the catalog for these? Um, okay, yin yang. No 2 by 2 monochrome. Um, so this is like we're going to be putting black and white squares, but we can't have um, 2 by 2 areas that are all black or all white. Oh, and they wrap around each other without cutting each other off. That's so sick. Um, so in some of our puzzles, like Nurikabe, we've got islands and oceans, and we make a rule that says something like um, the ocean must be completely connected, and the islands are the same size as the number that's on the island. Cool puzzle, lots of fun. No 2 by 2s. Also Nurikabe, no 2 by 2 ocean anyway. And then, but this one is like double Nurikabe. It's like two oceans against each other. Um, it shares some similarity with Nurikabe as well. The shaded region is fully connected and doesn't contain 2 by 2 in that puzzle. Um, and this is sort of like two such regions at once. I don't think I've seen yin yang before. Uh, it's going to be here. So all the puzzles that it's going through now are the examples it's taking are from this website, but has a big list of you know Nikodi puzzles, but also other Logic 2D grid puzzles. Um, so let's go here to the puzzle encyclopedia, I guess. I don't know what Ratzel? I don't know if I'm saying it right. What's a Ratzel? Riddle. I don't think we want logic riddles. Zahlenratzel? What's a Zahlenratzel? This is this is the side quest that we're on to understand. Okay, Zahlen number.
Salen Ratzol.
Okay, sorry if that was loud in your eardrums. All right, number puzzle, logic puzzle. Um, yin yang. Okay, so we start with this, and then we're like, well, we can't have any 2 by 2 of black or white. And this is enough information to fill in the whole grid. Both orthogonally connected areas, so we can't cut off black from white or vice versa. And we can't have any 2 by 2 areas. Lots of fun. I like it. Okay. Degree constrained spanning force. Yeah, this slant is fun. Um, yes. Unconnected. There are no cycles in slant. How does slant look? Let me back to Simon Tatham again. Uh, it's I think it's fair to say that Simon Tatham's probably, with some exceptions, the cream of the puzzles are in Simon Tatham. So here's slant. The rule is that we get only we're going to fill the whole grid with either forward or backward slash diagonals. And we have to obey the constraint that we're not sending a diagonal. We're doing degree matching, degree vertex matching. And so this guy says, don't send more than 0 into me. And this guy says, send exactly 4 into me. 4 is the max. And the other rule is we have to figure out something to put for this diagonal right here. And the rule is no cycles. And so with those pieces of information, all of this, we're going to be able to solve this puzzle. So look, we avoided this 0 and we satisfied this 2. Now check out what happened to this 3. We have to send all the edges into it. That one was already satisfied. This one was already satisfied. Sorry, I'm just laying edges on. So an interesting happens for the ones, 2 1s next to each other, and especially these ones on the edge. Look what happens if we do this 1. Then we have to fill in around it. And uh-oh, we've put a 1 into degree 2. So we definitely can't do this one. And by the same token, we can't do this one. 1 2 1 is an interesting one as well. So look what happens if we do this. So ignore the 3 for a second. Just pretend it's not there. We'd have to fill in this 1, and this 2 would be okay, but then the 1 on the other end would not be okay. So we actually have a rule, a general rule, that you can't send a line into a 1 followed by a line of 2's followed by another 1. You have to, um, on the outside of that 1, you have to fill in the numbers. So it always looks like this on a line of 2's in between 2 1s. And this is kind of a special case on the edge of that. It's kind of the same thing, just we can't fill in anything off of the grid on the other side. This is a special one where there's a 1 in a corner. All right, let's fill in some more. Don't know why. Okay, the VM having problems. We also have a general rule about ones that are diagonal from each other. If we filled in this slanty one next to them, then we would have to fill in all of the edges around them, creating a cycle instantly. So we can't do that. If we haven't chosen one of the slashes incoming for this one on the edge, we have to pick the other one. Here we've only got one place left to do this too. Notice that this cycle lit up right here. We can always kind of avoid that. Harder to do that on pen and paper. Like you have to be able to trace all of the cycles, and that might not be easy, especially if you're in this situation where you need to make a hypothesis. It can get pretty rough. So here we don't want to make a cycle, and here it is again. There you go. That's slant. Graph degree with connectivity in the Hashi family, i.e., this is like bridges and islands, I think, right? Yep, no cycles. Yeah. Um, yes, I I definitely consider them related, and the acyclic nature of the solution does feel very different to full connectivity required. Now, so far we have accepted all of its recommendations. Are we stupid? I guess we don't know. But I do think that it's making, like, for me, these are contextually appropriate recommendations. I'm not an expert on every puzzle type yet. Um, but every time that we've dove in and tried to understand what it's saying to us about each of these puzzle types, um, I think that we've like confirmed all of its stuff, like given ourselves that ground truth. And so, we've done how many of these? 10, 12, 11. I feel good about the other 20. Okay. H2Os. Disjoint paths with given terminals is K vertex disjoint paths problem. H2O is matching. The matched objects are edges, not paths. What does H2O look like? um, I don't see it in this list. Oh, maybe it's further down. Let's look at the entry. Given a grid of pre-placed hydrogen and oxygen, group them into water molecules. Oh, okay. This is like dominoes. Domino set. Okay. So, all right. I'll show you. Here we go. Oh, but we have to write in our own O's. Okay, interesting. Um, the hydrogen atoms that combine with the oxygen must be orthogonally adjacent. So it's very similar to tents too. Um, in tents, we have all of the trees, like the landscape, and we need to figure out where to put the tents so that there's exactly one tree for each tent, and the tents aren't too close together. And here, the oxygen atoms are playing the role of tents, and they need to be by two trees instead of one tree. Um, yeah, super similar to tents. Um, here is. We looked at tents before and summutate them. I don't know. So just imagine that instead of playing H2O, we're playing like carbon monoxide or something like that. And here we have all of the carbons, and we're looking for all of the um, carbon monoxide pairs. They're going to be next to each other. Um, and we also know that there's going to be no free floating ions anywhere, so we're not going to have a carbon without an oxygen or an oxygen without a carbon. It's all carbon monoxide. Uh, so look what happened in this column. So what I did was I lined out all of the ones where zeros. There's going to be none in that column, and then I lined out all the ones that aren't next to a tree because the carbons, monoxides have to be next to a tree. There was no option for any of these. We need all four of these tents in this column. Um, we need all three of these spaces in this three column. This one, this one. We're not sure if it's this one or this one, um, but there's a rule that if we're sure that it's in one of these two spaces, since we can't have tents next to each other, um, this obviously can't be a tent. It would take out this space. Uh, let's see. This chain of tents entries, it's got to end here because if we put another tent in here, we'd have three tents and only two trees. All right. We're just finishing off some columns here. This is now two. We don't know for sure if the tent's here or here. On this row, though, we know that there's exactly one tent. And we know that tents can't be adjacent. There we go. We need a tent adjacent to this tree, and that was the only option. And there we go. That's tents. And so H2O is very similar to that. Um, it's just that the tents are O here and need to be next to two trees. Let's go back and talk to it. Have we got? Oh yeah, just one more thing, of course. Like, is what's it called? Ah, don't know who to credit. We don't know who to credit. Um, um, I'm just gonna send it a link to this since it's not. It it might not be. Hmm. Let's look here. Tense. Don't see it yet. How do you say tense in German? Uh, English, German. We're trying to reverse engineer what it was found in Zelta. Do we have a Zelta entry? Ah, tense and trees. Tense. Zeltlogger. Um, all right, here we go. We found it. Okay. It's actually very similar to another staging puzzle. Zeltlogger. Tense. Intense. Tense is like H2O. Except instead of having one O for every two H's, um, we have we are we are playing carbon monoxide. We're playing carbon monoxide CO with one tree for every tent. Um, there are also um, row and column count clues. Should we mention Dominosa too? In this is also in Simon Tatham. Um, in Dominosa, it's like you're trying to assign the numbers in a grid to dominoes. They form pairs. So, for instance, like we know that we're going to have exactly one of each possible pairs of numbers, including doubles, 0 through 6. So there's going to be a 0, 0. It might be down here or it might be up here, but it's only going to appear in one of those places. And the job is to assign every pair of numbers in some configuration to, and so we can kind of, okay, that's nice. You can highlight them. So for instance, if we highlight the ones, we can see that there's only one pair of ones in the grid. So that's where the double one has to go. And you can kind of start using all this information. Like we could start looking for where are the 0 1s or where are all the zeros, and can we do a covering of all of the dominoes with our grid. Um, and this bears a passing resemblance to that, right? Because we're sort of thinking about how do I assign, with some of those numbers missing, how do I assign this H to be a pair with this H over here, as opposed to this H down here. And so there's some resemblance, some family resemblance there. Let's see if that has, if there's a credit that we can give for that one. to OS Adler. OSA. All right. Since this isn't in the catalog anywhere, I don't think. Well, I guess we can look real fast. Show me Dominosa. Oh yeah, here we go. It is here. Dominoes. Okay. Dominoes, also a staging puzzle. In, in Dominoes, in this puzzle. Every number must be assigned to a unique two member molecule. Uh, there is a covering um, from of all the possible two member molecules up to the puzzle size. So for any given number, it is guaranteed to be connected, but which connection to use is unknown. I said covering. I hope I used that right. uh, there's a bijection, I guess, is what you would say. For every molecule, there is a domino, and for every domino, there is a molecule. Dominoes is it's like the other puzzles, except all of the molecules have to be unique instead of matching, right? Okay. Okay. Milk tea. Milk tea. Each clue is a triple of circles that must be joined by horizontal and vertical line segments forming a T. Okay. But we don't know which T's to draw. And we can't cross. Yeah. That's fun. I mean, this is kind of like it's a lot like H2O too. It's a bit like H2O too, isn't it? placing the junction is like locating the O with a different um, constraint on the bond. However, I'm okay with you using the technical term as suggested. I think I put H20 instead of H2O, but it's gonna correct my typo. It's a good hydrate, I think, 90 minutes. Milk coffee. Let's go. Let's look at milk coffee. All right, draw straight horizontal and vertical line segments connecting orthogonally adjacent cell centers. Lines may not cross. I cannot guess what this looks like. Let's go look at it. Right, I should just be. We have a reference here. Should just be using it. Oops. Not sure what happened. Oh, I know what's happening. Um, I'm trying. I copied it with the Emacs, but we got to copy it with as if it's in the terminal. Copying Emacs, I'll be able to paste it in Emacs, but nowhere else. Okay. Milk coffee. Ah, interesting. Never connect black and white. There's one gray circle, and there's an even number of white and black circles. That's interesting. Isn't this fun? Um, it's what it's most similar to is Hashi again, right? Islands. Did I say that one right? Hashi or chopsticks, right? Yeah, it's much like it's very similar to okay. Yeah, it is. It's the same. Chopsticks. Hashi. Yeah. Yeah. Yeah, yeah. This is an interesting this is an interesting puzzle. Something like Hashi or Rockero. Uh, but yeah. instead of global connectivity, we need regional balance. Inter. Uh, Something like Hashiwo Kakero. Very similar um, rules for islands and non-crossing bridges. We need regional balance. The black, white, gray is nickel. I buy this argument. Okay. All right, we'll let it cook. $90 and we're halfway through these 30 judgments that we're being asked to make. I'm curious if we are mechanical similarities as well as mathematical similarities. Like, is there anything in here that see, I think that these two should probably be a little bit more similar than they are. A planarity constrained graph problem. I think that is true. Ah, and here it is, the planarity constraint right here. The visual payoff. Let's talk about this for a second. Um, for instance, before we talk about this one, for instance, uh, the planarity constraints in Milch Cafe. Did I spell that right? And Kakero make them pretty visually similar. But reading the entries, comparing the entries, might not bring that similarity across. Um, hmm. Is it possible we're missing other potential family relationships because we're writing the entries differently. What should we do to dig a little further? All right, I think before we started going through the instruction book for the world puzzle, we were going through the um, Nikori puzzles, the ones that we hadn't seen before. And I think that we might be able to figure out how far we got. Chokona, I think, is where we left off. Yeah, this was having to make rectangles um, in the grid, uh, like chocolate bars, with the constraint that each region has a certain number of cells that have to be filled in. And there's only one solution. I think we needed a lot of hypotheses to kind of get through this. But yeah, it was, I think, a really good puzzle. Bagu. Cave. Draw a single closed loop along the grid lines, which does not visit a grid dot more than once. Check. Numbered cells must be inside. How many cells inside of the loop are seen by looking north, south, east, and west? Oh, okay, so this is similar to numbers don't block the visibility of cells behind, but cells outside of the loop do. You cannot look through an outside cell to another inside cell. You can look through a number to other cells. This is cool. It's sort of like Slitherlink plus um, where is it? Range. So in range, you can only see so far from each of these numbers, right? If we said that all of these were open, right about here, we see the 13th, 14th number. So at some point we've got to block this 12. So say there was a square right here, that's sort of like a wall. That would cause this one to have only, C12 in both directions. And we just count those number of cells. 6 in this column, 7, skip it again, don't double count, 8, 9, 10, 11, 12. But if we put this wall here, then this one can't see far enough. That's sort of the idea of the game, that we need to satisfy all of the numbers at once. And there's a lot of tricks that we can use for that. 7, 8, 9, 10, 11, 12, 13, 14. The reason we had to do this was like this 14 can only see, well, even 6. 6, 7, 8, 9, 10, 11, 12, 13, 14. Actually, all of them. Because we could only see 6 in this direction, and we could assume, what if we did see 7 in this direction? Then everything out here, there's only one sort of more direction for this 14 to grow. And so we covered 3 directions, and then anything left over has to be opened. Yeah. This particular puzzle is 6 by 9, I guess. So we got 9 across, 10, 11, 12. That actually does satisfy the 12, I think. And we can't have 2 blocks next to each other. Yep, so from here we can just So that's this puzzle. And this one that we're looking at in Yanko is that puzzle plus a slither link. Pretty cool. I like this already. All right. Let's see if it's done thinking about that. Hmm. Open a schema design bead on a mechanic axis. Yeah, flat tags, yes. Audit the staged entries. I think it's going to be faster if I don't do this by hand. Um, let's do that. Okay, now it's gonna be busy for a bit. All right, let's head to our next. Hmm. Ah, here we are. Ral. Here, let's save this page. And yeah, I still never really figured out how to play takoyaki. That was like, I'm too smooth brained to understand takoyaki. Is that here still? Oh yeah, that was skyscrapers was no problem. We really zoomed through those. Okay, so as mentioned, it's a slither link where all the numbers have to be inside. Um, so one thing to note, I guess, is that if we didn't have if we didn't have these on the outside of the grid, then these numbers would be outside by definition, right? It's sort of like the outside is trying to get into our slither link, and so we can't let it in. Go. So all of these are just, yep, easy to see. I don't think that we have the same rule about node 2. Yeah, we can definitely have a couple of different grids next to each other, or outside cells. Okay, all right, cool. It's working hard. Okay. It is possible for these two cells next to each other, these numbers, to be linked. There's nothing wrong with that. It's like this one sees 3, and this one sees another cell off to the side. That's something that, like, when we're working on our range here, yeah, you can see that a bunch of numbers are kind of in a line with each other. 4, 5, 6, 7. This 11 looks kind of juicy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. We also have a situation here where all of the vertical of this 11 has been used up. So these 3, it's sort of like they don't contribute anymore. This is sort of like a horizontal 8 with no vertical motion. And so we know that anything next to it has also got a horizontal 8, right? They all share the same value. So this is an 8, 9, 10. And this one is going to be an 8, 9, 10, 11, 12. Yeah, I think so. Even though we don't know where this thing starts and ends, we know that it has to be 8 long because of this little addendum in the vertical direction. That's all we need for that. 5, 6, 7, 8, 9, 10. There we go. 1, 2, 3, 4, 5, 6, 7. That's it. Okay. So yeah, we're definitely looking for big numbers that constrain each other, numbers that are in the same line as each other, that kind of stuff. Here's our biggest number, 15. It can see 1, 2, 3, 4, 6, 7, 8, 9. It can definitely see this, 10, 11, 12, 13, 14, 15. So actually everything in here is visible and inside of the slither link. Now notice what happened here. This 2 has seen all that it can see, right? Because it sees another cell and that's its 2. It's completely satisfied. We're not sure yet if this, well, wait, let's count 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. This has to be inside the loop. And now we can start actually drawing this thing. Wherever we see the X's, we kind of have a chance to draw the slither link. Now we don't know yet if this is going to take a left turn or go straight. But here, let's look at this 3. We've actually drawn all the dots now. So it turns out it does go like this. If this were to turn, I guess one thing I haven't mentioned too is that the border between this thing is the border between inside and outside, right? And so I can't draw this border because these are both inside. I can't separate inside from inside. So that means that it has to continue this way. And I have to draw a border between inside and outside, wherever that's happening. So right here, here, here's a 3, already satisfied. Inside and outside. Here, here. 1, 2, and then this one's got to be 3. Remember, the whole edge of the grid is outside also. Um, yeah, we don't have a verdict yet on this one, do we? Oh, let's look at this 7. 1, 2, 3, 4, 5, 6, and this one has to be open. Okay. This would kind of imply that since we only have one slither link, if we put a dot here, we'd have to close this slither link into a separate loop, but it's all one big loop. So there's a dot here, there's an X here. And this is inside outside, and a very similar argument right here. This can't be a dot because if it did, it would close the loop. And same again here. All right. This 7, I only see 4 cells right now. There we go. This is a fun one. I like it. 1, 2, 3. Okay. Go. I mean, we're not sure yet, but this is shaping up to. We can't close this off. This can't be a dot. This is a border right here. I'm not sure exact. Oh, we can't close this off. So this has got to be like this at least. But it's possible that it either goes this way or it snakes around this way. Okay, let's see how this 10 is doing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, actually, all of its vision. There we go. All of its potential vision is there. Okay, so we did have to have it snake around. Gotta do this. We can't close this off because of the only one loop rule. Same right here. The 3 is done right here. The 4 is also done right here. Right. 1, 2, 3, 4. Be like so. Can't close this off again. And that last 4 right there. What a nifty puzzle. I like this one. It feels a little easy. Like we didn't have to make any tough choices. This 15 just kind of blew the puzzle open and we were kind of janitorial things. All right. I often get this janitorial feeling when we've sort of cracked the big inference of the puzzle and then we're just going around kind of mopping it. Okay. Mechanic axis. Mechanic tags. Hmm. It's good. All right. Let's read it. Whenever it writes me up a design proposal, I'm definitely inclined to read it. All right. Seems like we're going to have to redo the ingestion formula, and then we're going to have to backfill. Yeah. This is good. I think this is all. I think all of its examples are sound. Like I didn't go. I don't remember exactly what Yajidin is, but I remember these other ones pretty much. Um, it's making enumerations here. This, defining our enumerations inside of Markdown files that one just reads. It's like not the greatest data model in history, but it's fine. Yeah, this is, I think, good. Okay. Mechanics is action. Payoff is aesthetic. I think that's a good place to put it. I read the proposal. I do like the proposal. hmm Retro tag, it means backfill. Um, Pretty sure. It'll take an hour. Um, File a separate bead for retro tagging. That's fine. Okay, I'm fine with that. Our choices were to sort of interrupt what we're doing. Um, Putting it in QC is okay. Um, let's see if it alters the ingestion formula. If it does, then I think we're on the same page. It altered the schema, or it's altering the schema. Yeah. It's using the exact example that we used. Are they unrelated mathematical structures? I mean, this is an interesting thing when you start talking about puzzles, right? It's like we're talking about like constrained graphs of some kind. You know, it's got some adjacency. We got some edges that are orthogonal. You know, uh, catalog schema. It's describing mechanic tags now. See, it's saying that it's documenting that it's going to change the molecule for catalog ingestion. Ah, and there it is. Good. Okay, so this level of stuff, it's indicating to me that like it's keeping track of all of the details that I would be keeping track of. Sort of confidence building, in other words. Hmm. All right, 2 hour hydration check. To add in. I don't think I recognize that one. Don't know if I recognize either one of these. Doors. Decide for each interior edge between orthogonally adjacent rooms whether doors open or closed. Visibility runs through consecutively open doors. It's the number of other rooms that you can see through all the doors. That's fun. A sum over 4 maximal runs of open doors. That's fun. What an interesting. All right, cool. That does look different. That does sound different on the. Mhm. Region boundaries. Um, I like the mechanic tires. All right. Hmm. Let's see, where were we? Oh yeah, we really like Corral. Fun. I mean, Slitherlinks were good enough already, but now that we're paying attention to vision and inside outside, I mean, it definitely makes me wonder, like, what would this look like on, my favorite Slitherlink grid? I think I've already shown you is or loopy, as it's called right here. Right. This is definitely by far my favorite Slitherlink grid, and I've tried all of them many times. Um, but maybe not this size per se, but yeah, this setup is definitely my favorite. And it makes you wonder, like, what could we do with inside outside vision? I think you'd have to, like, it would be really hard to do in this particular one because the direction of the facing is kind of screwy. Uh, but say that we had like triangular, right? I think the vision in this one is actually well defined. So you could have the like you could set up this puzzle with a triangular grid and like the vision from each number would be well defined and you'd just be trying to do the one big loop. I feel like we've already looked at a triangle one together, so this is just me addicted to puzzles once again. All right. And there are probably some other ones that would also work. Uh, don't maybe. Seems like you could, like, can we define the vision for this one? I think so. It's sort of like this way and along this line, this line. It's a little complicated, but hexagon would probably work just fine. Yeah, I think the regular polygons, like the where the vision's unambiguous, um, that helps a lot. Okay, cool. It's interesting they've got it called Bagu and Kuro. Oh, that's interesting. Did you see what happened there? Um, I think we clicked on Dochi Loop, but we went to Creek. Yeah, and backwards. So, yeah, so those ones are linked backwards from each other. Don't know why. Okay. Rect slider. Is this, again, one of my not so favorites? This is more of like an optimization one, if I know which one we're talking about. Oh, no, maybe not. Did that work? I think it might have. Yeah. Oh, no. Okay. Move the black squares horizontally or vertically without changing direction in such a way that the black cells form rectangular areas greater than 1 by 1. A black cell with a number must be moved exactly as far as indicates. At most, one path through a cell. Okay. Yeah. All right. No, it's not the puzzle I was thinking of at all. All right. Let's see what it has to say about rect slider. solve state evolution. It's interesting that the objects slide. Um, Hiroimono. What's the one? It might be in staging somewhere. Yeah. Hey, wacky. Funny. Like the mispronunciation. But Boneson? They should have that one, right? I might be remembering like one of the it looks similar to Boneson Heabon. Motion planning probably covers both in a similar way. Um, Boneson. There's another one that's about moving things into regions, right? Which one was that? Yosenabe. Even here we go. I've never read this paper by Hordern in '86. Um, Happy that this exists. Like I said, there's like I enjoy the genre immensely, obviously. I'm gonna do my puzzle competition, obviously. Um, but there's a rich literature related to this that I haven't read. Even the stuff that I do understand about, you know, satisfiability and that kind of stuff. Um, you know, it's like at a graduate level. It's not like a doctorate or anything like that. So, um, good. Okay, great. Um, Hopefully, what we're doing by doing this too is we're getting at the underlying formalisms and the mechanics, and we're thinking, can we get all of the axes that we want to get to sort of fully classify any game? And so, ideally, we'll be able to, um, you know, not miss too many things when we think about similarity. Or what is the customer, what's the player going to think about when they think, is this game something that and also ran? I've already seen this before. I really, again, um, I guess I've got to learn more German and Japanese. All right. Regions, some partitions. Ah, okay, that's cool. So, it's sort of like sum of cell values. Well, I mean, um, this is a sort of degenerate version of this, right? Where um, if the area equals the clue, then that's like sum of cell values, where all cell values are implicitly one, right? Um, I think they're pretty similar. There is a special case of sum of cell values where every cell is implicitly worth one, and that's identical to the predicates on area. Um, height and weight, or height and width, the region's semi-perimeter. So the height and width of the region or the bounding box. Um, Different predicates on the region, I feel, are going to feel pretty different to the player. I'm with you on um, breaking out the something predicates into children of same the same. Um, yeah, polyomino size. Okay. Hmm. Hmm. RTT. I don't think I've heard of this one. At the very least, I guess, if I take nothing else away from this project, we'll have looked at tons and tons and tons of puzzles. Hmm. Ah, okay. All right. So there's an adjacency rule. We can have a number of numbers. Each cell has a sum of numbers. And if we use a number in one cell, then it can't be in any of the cells in the 8 neighborhood. That's interesting. That is different. It is kind of kaku, not kakudo, ken ken, kind of ken ken like. It's like you stuck a region in ken ken into, you stuffed it into a single cell, something like that. All right, what does it have to say about this? Multi-valued cells. Cells hold sets. That is true. That is different. Multi-valued cell. I guess the language on multi-valued cell is a little vague. It it's it seems like the solution is multi-valued, but of course the sum that is single valued is given information. Given mono-valued? Are we making up words here too? is is given is given information. Um, it feels a bit like a Sudoku or Kenken. Um, Yet having multiple numbers in each cell is yet pretty unusual. Excuse my yawn. We work with sums. 1 to 9. Yet having in using neighbors. Um, yeah. Maybe we can type I buy that it's deserves a class. Right. Under appreciated mechanic and formalism is an interesting target for novelty. Now I don't know how actually novel it is because I haven't looked at all 400 puzzles, but if it's new to me, then there's something to it. I would say. I guess we'll get around to this eventually. Is here. Sorry, I was. Is this German for source? Let's find out. Probably. Italian. How about German? Source. It was. Oh, it was. That's right. Context. Context clue. Seems like it's still working on that. Okay. Corral. As we said, big fan. Uh, let's continue through the encyclopedia of Nikodi puzzles. And if we get to one that we've seen before, then we'll skip it. Greek. Blacken some cells. Color them either black or white. Number indicates how many of the adjacent cells must be blackened, and all white cells must form a single orthogonally connected area. Little ocean here. Okay. Greek. There's nothing about 2 by 2 though. Notice. All right, got it. Exactly one same shape block across a border. So we saw LITS already, I think. It's about shading stuff so that we've got shape blocks. Tone Tombea. Assign one of 3 symbols to each cell. Oh, I've seen this before. One of the 3 symbols. They've used ABC, but could be triangle, circle, square. If a region contains different symbols, it must contain the same number of symbols of each shape. The symbols of a shape in a region must form an orthogonally connected area. So you can't split like the same symbol twice across the region. Each block must be adjacent to exactly one block with symbols of the same shape across a region boundary. So like this B is next to this B, but only one of them. And then it's got an A, and a C on its side. Got this A, but it's next to only one block of A's. Blocks of symbols of the same shape must not extend over 3 or more regions. So if we've got C and C, then this next one couldn't be a C. I feel like we've seen that before too. Like there's a crossword one where you can't make a word extend across more than 2 regions. Each block, so each subgroup, has to be adjacent to exactly one subgroup. Yeah, okay. I can feel myself starting to flag. One call out is that the shape here is about symbols. So for instance, the triangle, square, circle in the original design can be replaced with 3 distinct letters like A, B, and C without loss of generality. It's not about the shape that those symbols form as a group. The requirement in the rule is that when you have a group of a certain symbol in a bordered region, they should be adjacent to at most one group across a shared border. That uses the same. Um, so maybe we're not talking about shapes at all. All right. Then this is one of those strange like when we have these ambiguous meanings, like I think that using the word shape in these rules was probably like a huge mistake. uh, it's confusing to read the rules. Then you're like, and certainly the first time I read it, I was like, wait, did this shape of this have to be the same shape as this? Because these two are the same, like literal shape, just like rotated around each other. Um, but I couldn't. And then I was like, oh well, is this single go next to this single? But you can finally find a counterexample up here. Like this single B is next to 2 adjacent B's. But still, Mhm. All right. Okay. Uh, yeah, get. Okay. Cool. Yeah, I'd approve this. Assuming it's right. I'm just kind of assuming that it's right about clues about the boundary curve. Hmm. It's painful, I guess, to ah. Oh, right. It's wolves and sheep. We did talk about this before. Okay. It's sort of about the sidedness of a boundary curve. um, you're doing great. You're doing great, Cloud. Um, not right now. Okay. I guess I'm probably gonna make this the last one for the night since my brain no worky. We're 2/3 of the way through here. The oh, ghost stones. Ah, okay. I see. Really? Let's take a look. Oh, it's like, hey, that's my fish. um, hey, that's my fish is a game where you're playing against an opponent, or maybe more than one opponent. But you have these penguins starting on the board, and then they swim as far as they can a certain direction, and they hit a fish, then they stop and eat that fish, and it disappears from the board, and then you can kind of continue on from there. Um, Maybe I'm leaving out some stuff, but the idea is sort of like eventually you'll have eaten all of the fish that are adjacent to you, and you have to stop. And this is an interesting one where you're like, you have to figure out where to start and where to stop. Um, this is kind of an incredible puzzle, right? Because uh, say that you start here. Can you walk all the way through? Uh, and it's sort of like what else? I mean, it does share some similarities a little bit with bridges. Like there's only two ways to go from this stone. So either you have to start from it or they have to be connected. Um, you know, uh, Yeah, you can't turn around. It says 360. Turn around 360 degrees and walk away. It means 180, right? You can't go right and then you can't and then left. That's not permitted. So you have to go right and then turn. I guess you can go forward. So you're only allowed to go forward, left, and right. And the direction that you're going is like the direction to your next stone. I can see how this could be fun. You need to have some way to get to this stone. I can see how there's sort of a dead ending kind of thing here, where these ones, there's a dead end here and here. It wouldn't be obvious like which. Well, there's an asymmetry, right? Where if I start from this one and I start removing stones, then I can come back this way and pick this last stone. But I can't just jump from here to here because these stones are in the way. Like if I did go from here, I'd go this one, this one. I'd have to go here because it's the only one left, and then I'd be stuck. There's nowhere to go. So I'd know I can't start from here. So you must be like, well, how do I get to there? I've got to end there. So one of these stones is going to be my next to last stone. Interesting puzzle. I like it. Yeah, maybe you could use that to deduce that this is the starting one, and that this would be like the last one, and then sort of take it from there. Okay, what's it saying about Hiro Imono? Uh huh. Yeah. Yes, I see the relation. There is a hmm. Let's do one last Simon Tatham reference. It's find it signpost. The way signpost works is that we're going to travel from 1 to 16, um, but we have to visit every cell once and in sequence. And if we have an arrow, we can actually take it as far in that direction as we would like. We can skip things. Um, so we can start with easy clues like this arrow can only go in one direction. And we can't make cycles, right? Like we can't go back from A plus 1 to A. And we also can't visit this one twice, right? It only has one entry and one exit. So with all that, so here, for instance, this arrow can't go to this one. It has no entry. It can't go to itself, like so. There we go. And so if we follow this one has been hard for me to do sometimes. Like there's some puzzles that really lend themselves to, oh, you can just kind of follow a chain of inferences, and before long, you'll have figured your way out through the whole puzzle. But in this one, it usually turns into, oh, at some point, you need to start like guessing, trying a hypothesis, because it just gets too complicated to, um, make a huge leap from 1 to 16. And sometimes there are other clues that are written in, but in this case, there weren't. Um, so you start saying things like, well, I could make this my 2, but if this is 2, then this is going to be 3, 4. Then I need to sort of choose, does it go 5, 6, 7, 8? Or does it go before 5, 6, 7? Oh, this is an interesting one. This has to go here. Um, right, this B plus 2 couldn't go to this one or this one. because they already had parents, like some precedents. And then this one also, now it can't go to itself, and it's got to go right here. So if we pick this as our 2, then we'd be going 1, 2, 3, 4, 5, 6, 7, 8, 9, because we can't go to 16, 10, 11, 12, 13, 14, 15, 16. Okay, since that worked, we know that we're done. But you can see how that's you know, the experiment could have gone otherwise. Like, it could have been bad. And certainly as the game gets bigger, it gets harder and harder to make all of those connections. Does this have a Yonko call it pile pod arrow path? Let's see if that's in our. It might not be. Yep, pile pod arrow path. Um, Hopefully, I'm not butchering these German. I don't know how to pronounce the PF sound. I'm just saying file. File? File? Finish. And constrained by explicit directions. It is sort of a dual to Hiro e Ono because file fod explicitly allows jumping over unvisited cells, unvisited stones. Only and by explicit clues. Hmm. No reversal is kind of weird. I guess there aren't too many rules in the game of Go, but one of them is sort of no reversal like. There's a co rule that says we can't, if somebody captures one of your stones, you can't immediately recapture it to set up the identical board position. And that's called the co rule. And it is a kind of like, it feels sort of, when you get into the simplicity of the rules of Go and how beautiful patterns emerge from extremely small kernels, um, the co-rule does start to feel a little bit ugly because you're like, well, we had to do this to get rid of infinite cycles, and there are other weird things that start happening with infinite cycles, um, where you could have maybe 2 of these cycles going on at once, and you're kind of choosing between them and things like that. Okay. I guess I'm gonna pause it here. But the mayor doesn't need to know that. It's been working really hard. I hope that you have enjoyed this. Hope you've enjoyed our previous videos on World Puzzle Grand Prix. Highly recommend that you take a look at that and solve some puzzles if you like. And we'll be back tomorrow, probably finishing this part up. Hopefully, we'll be finally finishing up our catalog. And then we'll have a lot of good information here after we have like backfilled all of these mechanics and formalisms. And then I think that we'll have plenty of fodder to give to our inventor to try and come up with puzzle combinations that we've never seen before. So yeah, let's stop it there, and I'll hope to see you again tomorrow. Have a great night.